Hi everyone, in this video we're going to recap our understanding of limiting reactants. And we're going to start off by explaining what a limiting reactant is. We're also going to look at why we add some chemicals in excess and what that means. And then the final thing that you need to be able to do, which is the trickiest thing, is to be able to decide which reactants are limiting and which reactants are in excess using a calculation. And for that you're going to need to think back and use some of your knowledge about moles from year 9. Before we start, you're going to need the following things in order to complete this video. You're going to need a pen, some lined paper or an exercise book, and a calculator. You also need a copy of the periodic table. This should be provided in the resources within your assignment. If you don't have that available, you can find one in the back of your revision guide, and you should be able to also find one in the back of your homework pack. If you're still struggling, pause the video now and see if you can find one by searching in Google, or you can email your teacher and they will send you one. It will also be really helpful for you to have a highlighter pen. If you don't have a highlighter pen, don't worry. You could potentially use a different coloured pen like a red or a green pen, but if you don't have either of those, that's also fine. Pause the video now and go and collect the things you need. First of all, let's remind ourselves what happens during a chemical reaction. For a reaction to take place, two or more different particles need to collide. They need to collide with sufficient energy, and if you remember, this should be called activation energy. If those particles collide with sufficient energy, then a reaction will take place because the collision has been successful and a new product is made. A reaction will continue like this until one of the reactants has been completely used up. So as products are being formed, reactants are being used up until at least one of the reactants has completely been used up. Now, usually in a reaction, not both of the reactants are completely used up. Normally just one of them is. In the reaction that we can see now, the particles in green are still left over. We can also see that the orange particles have been completely used up. Now we have a particular term that we use for these reactants. We call the reactants that have been completely used up the limiting reactants. That means that the reaction will continue for as long as there are these reactants available to react, and as soon as those reactants, those limiting reactants, are used up, the reaction will stop. We call the reactants that are left over at the end, like these green particles here, in excess. That means that we have added more than we needed to for the reaction to take place. We say that those reactants are in excess. You might remember from your required practical in year 9, making salts, that you were instructed to add copper oxide, which is this black powder here, in excess to sulfuric acid, shown as this sort of grey solution here. You might remember that when you added excess copper oxide powder, that not all of it dissolved, and you were left with some particles of copper oxide powder undissolved and unreacted in the solution. That's why in step 3 you had to filter the remaining excess copper oxide powder, the black powder. That's an example of adding one reactant in excess. So in this example, the copper oxide powder was in excess and the sulfuric acid was the limiting reactant. We're going to quickly check our understanding of this. I want you to read the statement carefully and read each of the 3 options. Pause the video now for 20 seconds and choose your answer. When you've got your answer, restart the video and we'll check it. The correct answer is B. The limiting reactant is the one that is completely used up at the end of the reaction. That means that it's this reactant that determines when the end of the reaction will happen. Because as soon as this reactant has completely been used up, the reaction will stop. Let's do another quick check. Read the statement carefully, read each of the 3 options, and pause your video for 20 seconds while you choose your answer. Pause the video now. So you should have said that option A is the correct answer. The reactant that we say is in excess is the one where we have some left over at the end of the reaction. Just like copper oxide in your required practical. On the higher tier paper, you're going to be expected to not only understand what we mean by a limiting reactant and a reactant that's in excess, but you also need to be able to identify which reactant is limiting and which is in excess using a calculation. And in order to do that, you need to use moles. Now let's think back to year 9 and recap our knowledge of what we mean by moles. So in this reaction here, we've got a balanced chemical symbol equation. When we balance a chemical symbol equation, we add coefficients or numbers at the front of each particular substance. In this case, we can see 2. We don't see a number in front of the oxygen, but we can assume that there's 1 there, and we can see a 2 in front of the water molecule. What do these numbers tell us? Well, these numbers tell us the ratio of moles in that reaction. For example, in this reaction, the ideal mole ratio is 2 moles of hydrogen would react with 1 mole of oxygen to produce 2 moles of water. That's our ideal mole ratio. That's what we would expect to see. Now, if we think about making a cake, for example, when we make a cake, we need the exact ratio or proportions of different ingredients. For example, we should have the correct number of eggs, the correct amount of flour, the correct amount of sugar, the correct amount of butter, etc. If we get that wrong, then the reaction will be wrong and we will get a really horrible cake. It's a little bit like that in this reaction here. We've got an ideal ratio of each of those reactants that should react to give a particular proportion of products. So those coefficients, or those big numbers at the front, tell us the ideal ratio of moles. But what do we mean by moles? Moles are really big number of particles. A mole is a unit, just like we might use millimeters or micrometers, or we might use kilograms, or we might use seconds. A mole is a unit. But when we're dealing with particles, and we know that particles are really, really small, we know that there are going to be a lot of particles. So it would be really silly to use really large numbers, and it would be really, really difficult to do calculations that way. So we use 1 mole as a unit when we want to count particles. So 1 mole is equivalent to this number of particles. This is the number shown in standard form, but if you write that number out in full, you can see how large it is. We write that number out again, you can see how large it is. So we're talking about big numbers of particles. So we use a mole to make that really, really simple. We can calculate the number of moles by taking the mass of the substance and dividing it by this here. Now this is the mass number, or the relative atomic mass, and we'll find that number in the periodic table. Sometimes you might need to rearrange that equation. You might be asked to find the mass. Just like we do with all rearranging, all we need to do is move this number over here and we can find the mass. Or you might be asked to find the MR, but that's actually mostly really simple because it's already given to you in the periodic table. I want you to pause the video now, and I want you to please write down the following two equations that I've starred. I want you to write down this equation, and I want you to write down this equation in your books now. Restart the video when you've done that. Okay, so in this example, we're given some important information. First of all, we're told the mass of each of the reactants involved in the reaction. We're also given a balanced symbol equation here. Now, normally the examiner will give you the balanced symbol equation for a question like this. Now, the first thing that I'm going to do is I am going to rewrite that balanced symbol equation out so that I've got lots of space underneath to calculate the things that I need to calculate. Now let's just remind ourselves what this particular balanced symbol equation actually shows us. So the first thing that I'm drawing my attention to is the coefficients at the front of each substance. And remember, that tells us the ratio of moles. So in this example, we can see that for every 2 moles of copper, note that there's no number in front of the oxygen, so that tells me that there is 1 mole of oxygen. And the 2 in front of the copper oxide tells me that there's 2 moles of copper oxide. So our expected ratio is for every 2 moles of copper, we should have 1 mole of oxygen and we should have 2 moles of copper oxide. That is our ideal mole ratio. So if you were baking a cake, for example, you have to have the correct proportion or ratio of eggs to flour to butter to sugar, etc. If you get that wrong, then your cake is not correct. Just like in chemistry, you need the correct ratio of moles of each of those substances for the reaction to take place. So what we're going to do now is we're going to work out if the information in the question here gives us that exact ratio, or is it different. So the way that I would lay this out so that it's really clear and really neat is as follows. So the first thing and the easiest thing for me to identify is the MR, or the relative atomic mass of each substance. So that's going to be the first thing that I find out. The next thing is going to be the moles of each of these. And my end point is going to be to work out if the moles that I calculate along here match the expected or the ideal mole ratio at the top here. The other thing I have to remember is how I work out the number of moles, which I got you to write down earlier on. So I'm going to write this at the top so I can refer to it when I need to. Moles equals mass over MR. So I'm going to refer back to that whenever I need to. Okay, so let's work out the relative atomic mass of the things I need. Now, really, I don't really need to work out copper oxide. I should be able to work it out from just using copper and oxygen. Okay, so we'll keep it really simple and we're just going to work out the MR of these two. So how do I work out the relative atomic mass? Well, for that I need my periodic table. So the first thing I'm going to do is work out the relative atomic mass of copper. Nice and easy. I go to my periodic table and I find copper, and I know it's one of these metals in the middle, in the transition metals, and it's the larger number, the number at the top. So my relative atomic mass for copper is 63.5. So I'm going to make a note of that here. Now I don't need to do anything to that number because I can see here that I've only got 1 copper atom in the reaction. So nice and simple, my MR for copper is going to be 63.5. 63.5. Now let's do the same again for oxygen. But if you notice, oxygen, or a molecule of oxygen, has got 2 oxygen atoms in it. So we need to be really careful when we're calculating the MR of oxygen. So again, I'm going to go to my periodic table, and I know oxygen is on a gas, so it should be on the right hand side, and I should remember that it's in group 6. And again, I'm going to go for the top number or the largest number, and that tells me the relative atomic mass, and it's 16. However, as we can see, we have got 2 atoms of oxygen in each molecule. So we've got 16 of those, but we need to multiply it. So we've got 2 of those, and each one is 16, so we need to multiply 16 by 2. So my MR of oxygen is 16 multiplied by 2, which gives me 32. So I've now got my relative atomic mass of each of my reactants, and now we're going to use that to work out the number of moles of each reactant and see if it matches our expected ratio from the balance symbol equation. So remember, moles equals mass over MR. I've got my MR, but where do I find the mass? The mass, remember, is given to you in the question. So in the question, the information tells us that we've got 32 grams of oxygen and 190.5 grams of copper. So I'm going to use those 2 masses to work out the moles of each of my reactants. So let's do copper first of all. Remember, moles equals mass over MR. And remember that the MR that we've been the mass that we've been given in the question is 190.5. So I'm going to take 190.5 and divide it by my MR that I've already identified from the periodic table, which is 63.5. So that tells me, when I do that in my calculator, that I've actually got 3 moles of copper. Then I'm going to do the same thing for oxygen. So I'm going to do moles equals mass over MR. Remember, my mass is given to me in the question, so in this case it's 32 grams. And I've just worked out my MR of the molecule of oxygen, which is 32. So we can see there that the actual ratio of moles is 3 to 1. So we're going to compare that with our expected ratio of moles, and you can see that actually I've got more copper than I have oxygen. Oxygen is 1, which is what we'd expect, but actually 3 is a higher number than what we'd expect, so therefore it's the copper that is in excess, and we would say that the oxygen is the limiting reactant. Pause the video now and go back if you think you need to listen to that again. If you think you're ready to have a go at one yourself, then keep watching the video. So here's an example for you to try. I'm going to leave my worked example on the screen at the bottom down here. Set yourself a timer for 6 minutes and pause the video and see if you can calculate which reactant is in excess and which reactant is limiting. Okay, let's check our answer. So as with before, I've written out the symbol equation balanced, and then the first thing that I've done is I've identified the coefficients, which is telling me the ideal mole ratio, and I've written that underneath so it's super clear. So again, like with the previous example, for every 2 moles of copper, we should be using 1 mole of oxygen, which should give us 2 moles of copper oxide. I've written down my equation for working out the number of moles, and then I'm going to break that down into the individual components. So first thing I'm going to do is identify the relative atomic mass Just like I showed you earlier, I'm using the periodic table to do that, making really carefully, paying close attention to these numbers here, because that tells us how many atoms of each of the elements we have. So in this case, I'm going to multiply 16 by 2 because there are 2 atoms of oxygen. Then what I'm going to do is I'm going to check the question, which tells me the mass of each of those reactants that's used, and then I'm going to use that and my moles equation to work out the number of moles of each that I actually have used. So moles equals mass over mR. My mass in the question for copper, as you can see here, is 127 grams, and I've already worked out my relative atomic mass, and when I divide 127 by 63.5, that gives me a ratio of 2. Now you can already see that that matches our expected ideal ratio. So we know that copper, we've got the same ratio of moles that we'd expect. Let's check if that's the case for oxygen. So again, moles equals mass over mR. We've already worked out our mR in step 1. Now we can see what the mass is from the question. So 128 divided by 32 gives us a mole ratio of 4. Now we can see when we go back to our expected or our ideal mole ratio that that is wrong. It's actually much higher than what we'd expect. So in this case, we'd say that the oxygen is in excess, whereas the copper is the limiting reactant. Pause the video now and go back over that again if you got that wrong. Otherwise, you can continue on to your extended homework task.